Hello, and today for College Algebra, we're going to do some exponents and radicals. They kind of go together, so it makes sense to talk about them at the same time. Now here on this slide, just some general properties and some examples. Whenever we are multiplying with the same base, probably should use a different color, multiplying two numbers that are the same base, we would then add the exponent. So for example, 3 to the power of 1 times 3 to the power of 3, 1 plus 3 gives us 3 to the power of 4. Just like if I'm multiplying the same base, I add. If I divide by the same base number, I subtract the exponents. So here, I would get 3 to the power of 1 over 3 to the power of 3. 1 minus 3 gives us a negative 2. And let's hold on to that negative idea. Anything to the power of 0 is always, always, always 1. Now, if I ever have a negative exponent, it goes to the denominator. Unless, of course, it was in the denominator in general. Like if I had, 1 over 3 to the power of negative 2, this 3 to the power of negative 2 gets flipped, goes to the top. 1 times that's just going to be 3 to the power of 2. 3 to the power of 2 is 9. Kind of that reciprocal rule. I had a colleague who used to call this interaction right here the Drake rule because it starts from the bottom, now it's up here. Still like that joke. Now, if I'm ever separated two exponents by a parenthetical expression, this n gets distributed to every single term, and that interaction is, of course, multiplying. So I get 2 times 5 to give me x to the power of 10 in this example. This m gets distributed to everything. If they don't have exponents, they're 1, so 1 times the m is just the m. So we get a to the m, b to the m. Same idea here, outside exponents. This is still distributed, even if it's division. So you distribute the exponent when it is multiplying or dividing. If I had something like x plus 1 quantity squared, you cannot distribute. That is not okay. You would have to, as we talked about earlier last year, FOIL it out with how many exponent terms there are. And then an interesting thing is, as we talked about, is square roots are the same idea. If we remember, there's an index number implied there to be a 2, so that's always going to be my denominator of an exponential fraction. Whatever number or exponent is with this value right there, that becomes my numerator. So we get this idea of a to the power of m over n is the same thing as the nth root of a to the m. So let's take a look at some. Here I'm multiplying two fractions as we talked about in section 1. That is just multiplying straight across. So I get, I can distribute this. So I get 3 times nothing, so I'm just going to keep it the 3. I like to multiply the numbers together. There's no other numbers there. I get x squared times x to the third. So I would add those exponents. Okay. I also get y to the fourth. It's uncontested. I guess I did this in backward order. There's also this w to the third. So my numerator, I'm going to get 3, going in alphabetical order, w cubed, x to the fifth, y to the fourth. Now looking at the bottom, we have nothing to combine with. So we would just get 27 w x y to the seventh. Now some simplifying. I can, of course, divide both those by 3. And then I can look at these. They are the same thing on top of each other, so I get to subtract the exponents. 3 minus 1 gives me w squared up top. I can, of course, subtract these ones. 5 minus 1 gives me x to the fourth up top. And then, of course, I can do these ones. 4 minus 7 will give me negative 3, so I can make that a positive and put it in the bottom. So y to the third in the denominator. use properties of exponents, same idea. Multiply the numbers together. Negative 3 times 4 is negative 12. I am multiplying these two a values so I can add their exponents. There's no exponent listed, so it's implied to be a 1. So I get 1 plus 1. And then here we have b to the 4th and b to the negative 3, so I can get 4 plus negative 3. So my answer, negative 12, a squared, and b to the 1st, or just b. Exponent now here, so it gets distributed. Anywhere you see some other exponents, they get multiplied. So I get 2 to the 3rd, x to the 1 times 3, so x to the 3rd, y to the 2 times 3. So I get 2 to the 3rd, so that's 2 times 2 times 2, which is 8, x to the 3rd, y to the 6th. This 0 gets distributed. So I get negative 4 to the power of 0, a to the 2 times 0, which would be 0. Anything to the power of 0 is always 1. So I get 3a times 1, or just 3a. This 2 gets distributed to everything. We get 5 squared, x to the 3 times 2, so x to the 6. Y to the 2nd, that would of course be 25, x to the 6th, y to the 2nd, and there's no more simplifying we can do there. So radicals, interestingly enough, operate as this idea. Well, we already understand that add and subtraction are inverses. As we talked about a little bit on this previous slide right here, we get this same idea. Exponents and radicals are inverses. As we talked about earlier, this square root is the same thing as 1/2 as an exponent. So, just recall some perfect squares to work out and some interactions you get with. For example, if I'm multiplying two numbers underneath the radical, I can break them apart. So, if I'm trying to break down the square root of 72 in order to type that in my calculator, it doesn't have a perfect square root. But 36 times 2 is the same thing as 72, and the square root of 36 does exist. That would just be 6, so I can get rid of the radical right there, but I still have this square root 2 attached onto it. So that's one way you could simplify radicals. You can either divide using perfect squares, if you memorize them, or we break down like what's called a factor tree, or a factor cake, I've heard it, or factor ladder. So one thing, for example, let's say I'm doing 72, and I don't know 36 is off the top of my head. Well, I can look at this and see that it's definitely even, so I can do 2, and that would be 36. And let's say I forget that 36 is a perfect square. That's okay. I can break down 36 further into 2 and 18. 18 is 2 times 9. 9 is 3 times 3. Now, I'm doing the square root of 72, and I should remember that this index number is 2. So I need to find groups of 2 of the same number. So here, I have a group of 2 and a group of 3. Those numbers get taken out and multiplied together. 2 times 3 gives me 6. They're outside the radical. Anything we didn't circle stays inside the radical. Now, I like this trick because it works for square roots, but it also works for cube roots. So, for example, let's do the cube root of 72. You can follow the exact same process to 36, to 18, to 9, 3, and 3. Now my index is 3, so I want 3 of the same number. That gets taken out, and that goes outside the radical. Anything not circled, in this case 3 and 3, stay underneath the radical. And just like this 2 and 3 in blue were multiplied, these 3 and 3, because they're together underneath the radical, they get multiplied. This should be a cube root, I'm sorry. So the cube root of 72 is actually 2 times the cube root of 9. So this idea works for both. You could either, memorize perfect squares and divide, or even memorize perfect cubes and divide. Similar process. Okay. So again, no number. It's implied to be a 2. It's the default setting there. So 2 to the third would be 8. So a cube root of 8 has to be 2. 3 to the power of 4 is 81. So the fourth root of 81 would have to be 3. Some properties of radicals, as we said earlier on that second slide, this is the big one, where this value is the numerator and the index number is the denominator. Here we can break them up through multiplication or smash them together. Same thing we just experienced. And division also mathematically works the same way. So let's say, for example, we had, the cube root of 25 over the cube root of 5. We could recognize that 25 and 5 are easily divisible, and therefore I can just break it down to the cube root of 5 and simplify it that way. Interestingly enough, this rule right here interacts exactly like you think it should with the, goodness gracious, identity property of multiplication. So here, I can rewrite this, as we said earlier, in this form as a to the power of 1 over n. Well, I'm raising it to the power of n, so those things get multiplied. Well, what is 1 to the power of n times n? Or in this case, n over 1. That would just give me 1n over 1n. Well, anything divided by itself is always 1. So this kind of gets that identity as well. And the other last interaction that you often see is whenever you have the same radical, they can be treated as like terms when we multiply. So the 4 things you want to look out for like terms is you want same inside variable. You want the same variable on the outside, same outside variable. You want, let's see, the same number on the inside. Same inside number. Ooh, I think that's it actually. There might be another one. We'll come back to it if it comes up. So square root of 8 times the square root of 2, because they're both the same roots, we can multiply the 8 and the 2 together. 8 times 2 gives us 16. The square root of 16, of course, would be 4. Here, cube root of x to the third is obviously just going to be x, because if I were to make x to the third, how many groups of 3 can I make? Or if you want to think about it as rewriting, x to the 3 over 3, which is just x to the 1. Simplify the following, so 24. So if I break up the square root of 24 as the square root of 4 times the square root of 6, we would get 2 root 6. Here we get the square root of 75 over x cubed. We can do them both separately. So square root of 75 over the square root of x cubed. 75 we can break down as square root of 25 and square root of 5. X cubed, if I write out 3 x's, the index number is 2. How many groups of 2 can I make? Just the 1. How many x's are left inside the radical? 1. So I would get x square root x. And then 25 square root 5, of course, gives me 5 square root 5 over x square root x. Commonly, you don't want a radical in the denominator. So I have 5 square root 5 over x square root x. You typically do what's called, rationalizing the denominator. I'm going to multiply both by the square root of x. This creates x square root x squared in the denominator. And what that does is square root of x squared actually works out perfectly. We just showed it earlier. So now my new denominator, I didn't space these out very well, would be x from this x, and this gives me a second x, so my new denominator is x squared. Here, square root of 48 plus square root of 12, you can't do that unless your radicals are the same. They aren't. 48 and 12, different numbers. But we can simplify each radical. So for example, 12 I can break down as the square root of 4 and the square root of 3, giving me 2 square root 3. 48 I could break down as 16 and 3. So square root of 16, square root of 3, that would be 4 square root 3. And because now my radicals are the same, I can just add the numbers. 4 plus 2 gives me 6 square root 3. Here we have cube root of 48, x squared y to the 4th. I find it easier just to evaluate each of them separately. So cube root of 48, cube root of x squared, cube root of y to the 4th. 48, of course, I don't remember the cube roots off the top of my head very well, so I'm going to bust out the tree. As we said earlier, 16 and 3 gets us there. 16 would be 4 and 4, 2 and 2, 2 and 2. It's a cube root, so I want 3 of the same number. So my 2 goes to the outside, the 2 and the 3 stay on the inside. So I'm going to get 2 cube root of 3 times 2 for 6. Looking at my next thing, I have 2 x's. I can't make a group of 3, so they both stay on the inside. And here I have y to the 4th, so I get 4 y's. I can make one group of 3, so I can take that outside, and one's left on the inside. So this can be broken down as 2y cube root of 6x squared y. Again, if you want to do it the long way, or I guess the mathematically correct way, I can say it's 2/3. I can never break that down. But here, I'm going to get, 4/3. And that can be written as y to the 1 times y to the 1/3. Because remember, if I'm multiplying with the same base, I'm adding exponents. Well, 1 plus 1/3 gives me 4/3. So that's another way you can that's the way you can do it properly. I just kind of like the visual shortcut of the y times y times y times y. Oh, rationalize the denominator. Looks like I got a little ahead of ourselves. Whenever I have a denominator that has a radical, I typically want to simplify that a little bit. Often, I'm going to end up multiplying by something that's going to clean that out. But you need to do it to the top and bottom, because if I'm multiplying by the square root of 3 over the square root of 3, that as a concept equals 1. So I'm not changing the value of the of the rational expression fraction. So here, I guess do we not have an example? That's it. Sounds good. And simplifying rational exponent expressions, you can break them down in a couple different ways here. So I have square root of 3xy all to the 5th. I can just treat this as my m expression, and my n equals 2. And put that out front and just call it a day there in that a equals m over n form. But here, though, I have different x's. So we can treat this term as x to the 3 over 4, and this x is just x to the 1. Well, I'm multiplying with similar x values, so of course I would just add the exponents. So I get 1 plus 3/4. Now, how many fourths are in one whole? That would, of course, be 4/4. So 4/4 plus 3/4 gives me 7/4. So my final answer there would be 2x to the 7/4. Thank you for listening, and I hope you have a wonderful day.